Helen is currently a professor emeritus at Stanford University in the Department of Psychiatry and Behavioral Sciences, where she has been a faculty member for several years. Helena also holds a position as an adjunct professor in the Department of Psychiatry at the University of Pittsburgh, where she held a joint appointment as a professor since 2009. She earned her BA in mathematics from Smith College, attended Manchester University on a Fulbright, and received her PhD in statistics from Stanford. Her specific research interests include improving RCTs, assessment of reliability and validity of diagnoses and clinical measurement, and she has published extensively in the behavioral and clinical literature and statistical literature. Dr. Kraemer has received the Harvard Prize in Psychiatric Biostatistics and Epidemiology, the Andrew C. Leon Distinguished Career Award, and an honorary doctorate of science from Wesleyan University. And she's a member of the Institute of Medicine and the National Academy of Sciences. In her retirement, she continues to serve on several editorial boards and consult on research projects, and continues to write and publish books and papers. So, given her status and her expertise, it is no surprise that many here have collaborated with her. And so without further ado, I please welcome me, and please join me in welcoming Helena. Thanks.
Well, thank you so much for inviting me. It's always a joy to come up to UCSF, which I, as you know, have done frequently over the years, both in collaboration and in teaching. And because I'm not always the most gracious guest, I'm going to warn you in advance that if I don't say something that annoys you, irritates you, or at least intrigues you, I will not have accomplished my purpose today. I'm going to talk about controversial approaches in psychiatric research, which means, of course, that there's a lot of disagreement about what I am about to say. I will start with the contentious claim, first of all, and that is, I make a difference between biological experimentation and medical research. I think the goal of medical research is to reduce the burden of illness on patients. This may be directly, as in a randomized clinical trial or a prevention study or something, or maybe more distal, like looking at the biological substrates of diagnoses, etc. But ultimately, it should be to reduce the burden of illness on patients. And you're going to see that this is a theme that I am going to follow as I go through these various issues. Why are these goals not being realized in mental health research? You might question whether they are not being realized in mental health research, but then you're aware of the fact that most drug companies no longer put a lot of effort and money into developing psychotropic drugs, that many people claim that there hasn't been an effective psychotropic drug developed in the last 30 years. We don't know any more now than we did 30 years ago about how to prevent mental illnesses. So if, at the very least, progress has been relatively slow. And there are probably a lot of reasons for this. But the two reasons that I'm going to talk about today in particular are two that we could very quickly solve. One of them is the careless use of scientific language. Scientific language is very precise. It has to be very precise. If I use a word like variance, and I use it in a scientific sense, you should understand the same thing by the word that I mean by the word. If we use the same word for different concepts, if we basically use the word for things that are very different from the precise meaning of the language, it's going to introduce confusion into the literature and confusion in research, and I'm going to talk a bit about that. The other one is a particularly annoying problem, and that is when you point out that there is something that is questionable done in a research project, and the response is, but that's the way we've always done it, or that's how everybody does it, or that's what the reviewers told us to do. I can remember when my kids were preteens, and now my granddaughters are preteens, that basically if they came and said, Mom, I have to have that because everybody else has it, they knew that they had already lost the argument. They had to give me a better reason than that. To me, I find it appalling that researchers who are intelligent, trained, experienced, committed, etc., would basically say, I am doing it knowing I'm probably wrong, but everybody else is doing it, so it's okay. It's not okay, I'm sorry. A bit of history, where all this worry came from, started, was when I was a member of the MacArthur Network, which was focusing, I think the title of the network was psychobiology, no, it was developmental psychopathology. And the goal of the network was to develop ways of identifying kids who were likely to very early develop psychopathology, early being pre-adolescent years, to try to come up with some sort of ways of possibly preventing early development of psychopathology. And the network included a number of researchers in a number of different fields from a number of different countries who were really expert in the field. And we reviewed what was at that time a tremendously expansive literature on the subject to find out that we didn't know very much about what was going on here. The research papers that we were finding contradicted one another. Some of them seemed to come up with what are totally meaningless or uninterpretable results. It was really very deflating. Part of it was because the terminology that was used in risk research was so inconsistently being used, and I'll talk about that in a minute. Part of it was part of this controversy I'm sure you're all aware of, and that is people overvalue p-values, where p-values really don't tell you that terribly much. We really, really need effect sizes that clinicians can understand and use. And then there is this business of moderators and mediators, which will be the focus of a lot of my subsequent discussion. Prior to 1986, I had heard the terms moderators and mediators used all the time. They've been around forever. But there were no specific definitions. Meaning it meant whatever somebody meant it to mean in the context in which they used it to be terribly much. And it had no effect that I ever saw, at least, on medical research. In 1986, and it wasn't in medicine, it was in social psychology, Barrett and Kenny published a paper, which has to be one of the most cited papers of all time, in which they proposed definitions, conceptual definitions for moderators and mediators, which made it very clear why these concepts were important. It didn't actually get over into medicine at all. But the problem was that it became quickly apparent to those of us who were trying to use those definitions that there remained a great deal of ambiguity. The concept seemed right. It was the mathematical definitions that somehow or the other, what can I say, leaked. Basically, the distinction between moderators and mediators and how they related to everything else in the field was just not very clear. So this MacArthur Network that I just mentioned in the 2000s, in late 1990s and early 2000s, tried to take the concepts, not change those, but tried to expand the definitions so as to remove the ambiguities that we were seeing. And in addition to that, because the Barrett and Kenny model is very tied to a linear model, to try to expand the context in which it could be used. Not everything is linearly related to everything else. So we are in a very different situation today. There are a lot of people who are using the MacArthur Model definitions in medical research. Social psychology continues to use social psychology definitions. Those of you who are trained in psychology may have been exposed to the Barrett and Kenny method, and I'm going to ask you to change, which is always difficult. So these remain controversial just because it's sort of in a period of transition, still, even 15 years after the proposed MacArthur model. So let me start with what is already in the literature. Yeah, I'll start there. Statistical significance versus clinical significance. You probably are all aware if there is a movement to ban the p-value. Yeah? There is actually a journal that banned it for a year or two under one particular editor. I don't normally read the journal, but I did during that period of time. I thought it was a great natural experiment. And I thought the quality of the papers went up during that period of time because the researchers who were publishing papers had to think through the issues. They didn't just knee-jerk p-value, a couple of stars there, which tells you absolutely nothing. So just to remind you, p less than 0.05 or 0.1 or whatever it is, or 10 to the minus 37, I saw one recently, means that the sample size was large enough to detect some deviation from the null hypothesis. and all others is often random. That does not mean that what you found was big, important, exciting, or anything else that would warrant putting stars all over the place. You need something more to make that kind of a claim. Not statistically significant means that the sample size was not large enough. It could mean that the design was not very good. It could mean your measures weren't reliable enough. It could mean that the sampling wasn't done well enough. It could mean a lot of different things, but it is something wrong in the decision-making in the particular study in which it's being reported. Alternatively, it could be not in the study decisions that were made, and often this is true. It could be because the rationale and justification for this particular study is based on a literature where there are a lot of false reports. And so it may have been that the researchers who proposed this study were misled in the first place. They designed a great study, but the rationale was bad. The solution to both of these problems is basically to present an effect size. If you want to convey the notion of whether this is big, large, exciting, whatever, give us an effect size that we can interpret. And give us a confidence interval to show us how precisely you're estimating this. And you can do this either in addition to a p-value if you're really fixed on reporting p-values, or you can do it instead of a p-value if you want to ban the p-value. I have no particular feelings about that. Just give me an effect size, and I'd be happy. Now, what the effect size is a matter of contention itself. I won't go too far into this. If we're talking about effect sizes for risk studies, the most common one is the odds ratio, which is a totally uninterpretable effect size. Have I offended every epidemiologist in this? The odds ratio of 1 means random association. The odds ratio greater than 1 means positive association. Less than 1 means negative association. But the value of the odds ratio otherwise gives you no information at all. An odds ratio of 10 may be much weaker than an odds ratio of 1.5. It doesn't make any sense. There are a lot of measures of potency of risk factors available that do make a lot of sense. They usually depend on the relative importance of false positives and false negatives. Odds ratio is not one of them. In randomized clinical trials, most people use Cohen's d, which happens to be close to my heart. But it really is meant for normally distributed outcome measures, and most measures are not normally distributed. So I would prefer something like success rate difference, number needed to treat, which are measures of treatment outcome that basically can be used whatever the distribution of the outcome measures are. But this is a topic that really needs a lot more discussion than we have ever given it before. Another preliminary is two-factor association. Almost all medical research problems can at least be expressed as a two-factor association. Treatment choice versus outcome, presence, absence of a risk factor versus onset of the disease, this brain area versus that brain area, this gene versus, there are a lot of them. And it is a terminology problem. If what you can show, and science is all about what you can show, not what you think is so, if you can show two factors to be related to each other in some way or the other, the appropriate term for that is correlates. A and B are correlates of each other. If two factors are correlates, and you can also show that A precedes B in time, then it is appropriate to say that A is a predictor of B, or to say that A is a risk factor for B. The problem, and this was the problem we met in the MacArthur Network, is that many people use the word predictor for anything they put on the right-hand side of a regression equation. And many of those predictors happen simultaneously with the thing it's predicting, or happen afterward, and sometimes may be a consequence of it. It didn't take much of Latin to realize that predictor means before, say. You really do have to have the time precedence before you use that word, otherwise it's really going to be a problem. The same thing is true of a risk factor. The risk factor has to precede its outcome, otherwise it's not a risk factor. If it's a risk factor, A is a risk factor for B, and you can show that no other factor exists that explains away the association between A and B, then it is appropriate to call A a causal risk factor or a cause of B. I put an exclamation point there because this is one damn hard thing to demonstrate. In medical research, the general rule is no causation without manipulation, which means that the gold standard is do a randomized clinical trial in which you manipulate the risk factor and show us that it changes the outcome. The problem in the literature is that a lot of people do cross-sectional studies in which you can only show that things are correlates of each other, but that then jump to the inference that something is a cause of another thing or a risk factor for another. And this causes a lot of, I'm using the word carefully, a lot of problems because people who read those papers may take those claims seriously and there's no documentation for them at all. So, according to these definitions, all causal factors are risk factors, not all risk factors are causal factors. All risk factors are correlates, but not all correlates are risk factors. And I can tell you that if you, in fact, reread a literature, and this has been done in a couple of contexts, very carefully separating out the cross-sectional studies, very carefully separating out whether they've shown things to be risk factors now, whether they have shown things to be causal or not, and focus on the things that are using the language correctly, you will find that a lot of the errors are being removed from the literature. This is the source of a lot of problems. Let me go back here. I wanted to make one more point before I left here. All the comments that I have made about correlates, risk factors, and that are population specific. This is always true. If you can show that something's a risk factor for one population, that doesn't mean it's a risk factor in all populations. So for example, Ellen Cassie's example, being married is a risk factor for suicidality among teenage girls. But being married among 30 and 40-year-old women is a protective factor against suicide. So this is a case where the polarity is actually reversed. So don't generalize beyond the population that is being studied. That is a problem in itself. One of the things that we quickly discovered in the MacArthur, even after we sort of cleaned the literature out, for our purposes anyway, is that there are very few things which you can resolve, very few problems you can resolve by only understanding a two-factor association. A treatment, you can show an association between choice of treatment and outcome, like a randomized clinical trial. That doesn't necessarily mean that everybody within that population actually has exactly the same relationship between treatment choice and outcome. You could show that something was a risk factor, but within that population, some of them might respond very strongly to the risk factor, some of them not at all, and some of them might even respond negatively. There are always individual differences among the people in the populations we are studying. And we probably, in most cases, will not understand whatever the phenomenon is we're studying until we recognize where those individual differences are coming from. So be careful about the population. I can't prove this. I was told this when I was a graduate student by my statistics professor, who said, if you can prove a theorem in one dimension, do not ever expect that it's going to generalize to 2 or 3 dimensions. If you can prove it in 2 dimensions, there's a chance it might generalize to 3, but don't count on it. But if you can prove it in 3 dimensions, it's going to work for all dimensions. And I'm going to make the claim, without proof, that if you can figure out how to process 3-factor associations, you can figure out how to process all more complex, more variable associations. And it's a little like putting together a jigsaw puzzle. It's not easy, but it can be done. Now, I'm going to start with B as a proxy risk factor. This is the 3-factor associations, the first example. B is a proxy risk factor for A with respect to some outcome measure. B and A are both risk factors for A, and O is an outcome measure, so B and A both precede the outcome. And the concept here is that very frequently when you see a correlation between 2 factors, one of them may be, one or both of them actually, may be standing in for something completely different. So it's a stand-in for something that's missing from current consideration. The criteria for establishing a proxy risk factor is that there's no temporal precedence, or A precedes B. A and B have to be correlated, they have to be correlates of each other. And when you consider both A and B in the prediction of the outcome measure, only A matters, B does not. What do you do if you find a proxy? Set it aside. And there are a lot of proxies that we have to deal with. And to give an example, my daughters and granddaughters strongly object to this example because they were all very good softball players. But generally, ball throwing ability at the age of 10 is much better for boys than it is for girls. Boys usually can throw it harder, faster, stronger, etc. We know from research that gender is a risk factor for teenage onset depression as well. Girls are much more likely to develop depression in their teen years than are boys. If you ignore gender and you correlated ball throwing ability against onset of depression in your teen years, you might well find a correlation. This is not a reason for proposing programs to teach girls to play softball better in order to prevent depression. I can guarantee you it's not going to work. But if you put both gender and ball throwing ability in, if, for example, you correlated ball throwing ability only within boys or only within girls, you will find probably it has no relationship at all. That's because ball throwing ability in this case is a proxy for gender. And as I say, there are a lot of these, and we have these huge data sets where most of the variables there may be proxies. It's best to clean them out and leave the things that really matter before we can understand this. A second three-factor association is when you have two factors which are overlapping. This comes from a fact you all know, which is that particularly in psychiatry and psychology, there are a lot of things we can't measure very well, and so we measure it 10 times badly. Right? And the idea is that somehow if we have 10 bad measures, we can somehow figure out what the good measure is. That is both true and false. If you use those 10 measures separately, you're only going to confuse the issue because all you're doing is enriching the errors. On the other hand, if they are in fact measuring the same thing and you judiciously combine them to one, you probably would have an improved measure of that particular construct. So reducing it to one would be a good idea, and that's where overlapping comes into the picture. So we have two factors to measure, the same core construct that's related to the outcome measure. The criteria is no temporal precedence, they have to be measuring the same thing. A and B have to be correlated. And if you consider both A and B, both of them matter to the prediction of the outcome measure. And what do you do about that? Somehow remove the redundancy. Now, you're hearing a message here from both proxies and overlapping, and that is having too much information, not information, the information's great, too many measures in your data set. That individual measures don't give you more information. You are far better off by reducing the data set judiciously and finding out what's really going on. Practical example, this is from Merrill and Essex work. We're talking about preteen kids. Internalizing and externalizing are generally comorbid. They're very heavily comorbid. There are studies that show that kids who show internalizing disorders, if you follow them in time, will also show externalizing. Kids who show externalizing will eventually show externalizing scores. They go from one to the other. The risk factors for internalizing and externalizing tend to be much the same. The one thing that consistently differentiates it is that girls tend to be internalizers and boys tend to be externalizers. But if you're using these two scores for prediction of mental health 5 years later, basically what Marilyn did was found that they were overlapping. I realize the symptoms on themselves are very different, but in terms of how they relate to the outcome measures, they were overlapping. They were correlated with each other, and they, basically, they both mattered to it. So what she did was she actually combined internalizing and externalizing to a general measure of symptoms, and the remaining information turned out to be only gender specific. And now we get to the meat. A moderates B on O. This is a Barron and Kenny concept. Barron and Kenny did not deal with proxies and overlapping. A moderates B on O if A suggests on whom or under what conditions B works on O. The criteria are that A has to precede B. The moderator always precedes that which it moderates. A is uncorrelated with B. And the effect of B on O, on the outcome, depends on what A is. Simple example, if you have to a randomized clinical trial and you find that the treatment effect is the relationship between treatment choice and outcome. Treatment effect is different from men and women, then gender moderates the effect of treatment on outcome. The action here is to stratify the population. It may be that the population is either, if this were a population defined by a diagnosis, for example, this might be different subtypes of the diagnosis, which would be very informative. Or it may be that the diagnosis itself, if it's like a DSM diagnosis, is lumped where it should have been split. But somehow or the other, this B is working differently in these two populations, which might suggest you might want to look at them separately to stratify them. Caspi hypothesis is my favorite example of this, which shows, or which hypothesizes, because I don't think it's ever been proved, serotonin transporter gene moderates the effect of life stress on subsequent onset of depression, meaning those with a particular genotype at that locus will respond to stress by developing depression. Those with the other genotype at that locus, stress doesn't have that effect at all. And this is important because if you're going to do prevention by manipulating stress in some way or the other, it's no use doing it on the genotype that doesn't respond to stress. You would focus here. And if you did it on everybody, you would dilute the effect because manipulating the stress in the people who aren't responding to it isn't going to make any difference. So that's an example of moderation. And it's also an example of what may be true of every gene that has been considered as a susceptibility gene. Susceptible to what on what? The gene is a moderator of the first what of the second what. More meaning. B mediates the effect of A on O. The concept here, again, Barry and Kenny, B mediates the effect of A on O if B explains part or all of the effect size of A on O. The criteria, you have to show that A precedes B, that A and B are correlated, that when A and B are jointly considered in prediction for O, only B matters. Notice if only A matters, it's proxy, right? But if only B matters, then you have total mediation. And if both A and B do, it's partial mediation. And what does this suggest? Well, don't draw any causal inferences here, but it certainly suggests the possibility of a causal path leading from A to B to O. And so then it becomes very important. I will show you this MTA study result in more detail later, but the choice of treatment in a randomized clinical trial had different effects. In this case, it was for ADHD kids. It had different effects on compliance. And compliance explains some of the differential treatment effects on the outcome measure, which was reduction of symptoms. What's the message here? Well, if you want some of those treatments to be even more effective than they were, maybe you should include components in your revision of the protocol for treatment that might actually increase the compliance. We're trying to figure out why the compliance isn't as high as it was and somehow change it. It might give us access to improved treatments by using the data from our randomized clinical trials more effectively. Same thing in risk research. A and B are independent with respect to O. The concept here is that A and B simply tap completely different constructs, and they act independently of one another. The criteria, A and B are not correlated, they're independent. And A neither moderates B nor B moderates A. And the action is very simple, keep them both. Because they're separate and they act separately. Gender and ethnicity as risk factors of obesity is one example of this. Certain ethnic groups are more likely to, at higher risk for obesity. Women are more likely to be obese than men, and they tend to operate independently as far as I've been able to see. So those would be independent factors for O. Now to summarize, I'm going to have to look there because I can barely read this one. I wanted to make 2 points here. One of them is just to summarize what I've just said. So I'm repeating the definitions I've already given. But also I want to assure you that I've exhausted all the possibilities with these particular criteria. So the first question, you have 2 risk factors for an outcome. The first question, is there temporal precedence between A and B? And if the answer to that is no, the second question is, are A and B correlated? If the answer to that is also no, then A and B are independent risk factors. If the answer to that is yes, there's one more question. Do both of them matter? If the answer is yes, they both matter, then they're overlapping. Combine them, try to reduce the data set. If the answer is no, then one of them is proxy to the other, get rid of it. If the answer to the first temporal precedence question is yes, I'm going to label the thing that comes first A before B. The next question is, are A and B correlated? If the answer is no, one more question, do they have an interactive effect? If the answer is yes, then A moderates B. If the answer is no, A and B are independent. If it's moderate B, you might want to consider subdividing the population and looking at the subpopulations separately. If the answer is yes for temporal precedence, and yes to they are correlated, the next question is, do they both matter? And if the answer is yes, then B mediates A, consider a causal tap. And if the answer is no, then B is proxy to A. And what I've done is I've shown you, first of all, there are two routes to independence and there are two routes to proxy, but this totally distinguishes all of these. The criteria are unambiguous as to which you classify into which, if you knew the population parameters, and so you would try to do this with samples. What's controversial about this? Well, it's the original Baron-Kenny linear model that causes the problem. It was originally discussed in social psychology, and I have found over the years that the standards of research differ from one field to another, largely because I've worked in so many fields, and I find I have to change as I move from one to the other. In social psychology, what they frequently do is they hypothesize a certain model. And if the data does not contradict the model, that's taken as documentation that the model is true. This is not the way we do it in medical research, where whatever you're hypothesizing or whatever model you're proposing, you have to prove beyond reasonable doubt to be true, or else it should not be accepted. But in any case, the results, the specific definitions that Baron-Kenny didn't work very well when we try to put them into medicine. The linear model, and I'm switching from A to B to M to T here. T is the target, and M is the moderator or mediator, with O being the outcome. The specific linear model is this one, that M is linearly related to T, and that O is linearly related to Tm in the interaction Tm. The problem, of course, is if T is binary, like a choice between two treatments, the first model is going to work pretty well. But if either T or M is ordinal, you've got to worry about those linearity assumptions here, and so strange things can happen. But I have to say that 90% of the time, the MacArthur Model also uses a linear model, so this is not to try to discourage you from it, it's just warning you to be a little careful. But I will tell you this, and that is, I hope I'm not insulting anybody here, but I'm going to say it anyway because I find it, a lot of people don't know this. And that is, if you are using a linear model like this one, with an interaction like this one, you better be very, very sure that you've thought through how you code the data, because how you code the data totally changes the results. So I'm going to give you a side lesson on centering. That is what I've just said. If T is binary and you're doing moderator-mediator analyses, code it plus a half, minus a half, not 1, 0. And if it's ordinal, center it at the mean or the median. In other words, instead of taking the variable number, subtract off the mean or the median. And if M is ordinal at the time, code it according to what is known at the time of T. So moderators, since M precedes T, centered at the mean or the median, plus or minus a half if it's binary. And if it's a mediator, since the mediator has to be a change or an event that happens after T, centered at 0. That's the other one. Now, my horrible example of this, and I hope it sticks in your mind the way it's stuck in mine, was a randomized clinical trial being done for Alzheimer's patients. It happened to be a drug study, a drug versus placebo, in which they were hypothesizing that the age of diagnosis of Alzheimer's may moderate the effect of treatment, and I can't remember which way it was, whether the early onsets were more likely to respond or the late onsets, but they were hypothesizing a difference. And they did the analysis by coding the treatments as +1 and 0, which a lot of people do, and they coded the M as chronological age. And when you do that, in this particular thing, let's see if I can go back to the model, if you do that, then the treatment effect, the beta 1 in this model, is the effective treatment on patients who are born having Alzheimer's disease. Because that effect is the effective treatment for those for whom M is 0. Ain't too many people who are born with Alzheimer's disease. So it wasn't a particularly useful result, besides which it was terribly confusing. Instead, what they should have done was they should have coded as deviations from, let's say, 65 or 70, whatever the average age of onset is of Alzheimer's. They also coded T as 1 and 0, in which case beta 2 was the slope of outcome on age for the control group, for the placebo group, which was exactly the opposite of what they were really interested in. They didn't think placebo response was related to age. They thought drug response was related to age. And so they got exactly the wrong answers by dint of coding. If they coded a plus or minus a half and they coded M as deviations from the average, then the beta 1 is the treatment effect for the typical subject, meaning at the average age. Beta 2 is the average of the two slopes, and beta 3 is the difference between the two slopes, and everything is clear. Century. Why are the Baron, Kenny, and MacArthur approaches produce different results? Why? What was this ambiguity all about? In the Baron and Kenny approach, M moderates T. All you had to do was prove that there was a non-zero interaction effect in that linear model. There was no specification of temporal precedence and no specification of association. The absence of the temporal precedence meant that every time you proved that M moderated T, you had also de facto proved that T moderated M. The directionality was totally ambiguous. The social psychologist said that's all right because it depends on what your model is, what your theory is. Medical research, no, it doesn't work that way. The MacArthur differs. It has exactly the same analytic criteria. You have to show the interaction, it's not 0. But because it has the temporal precedence and the correlation criteria, that removes that directionality ambiguity. M mediates T. The original Baron and Kenny definition had no temporal precedence criteria, but I've said that it does here for this reason, and that is, in talking with Kenny over the years, he keeps saying to me, now come on, it's logical that you have to have the temporal precedence. After all, it's mediator. Doesn't that mean in between? So I will say that at least Kenny concedes that there is a temporal precedence criteria. Both of the approaches require that you prove the correlation between the mediator and T. The major difference here is that in the Baron and Kenny model, the analytic criteria, you assume that there is no interaction. In the MacArthur model, you have to prove it. If it's not there, you have to prove it. So in the Baron and Kenny approach, you assume no interaction, and you simply prove that the effective M is non-zero. In the MacArthur approach, you have to prove that one or the other or both of them are non-zero. That removes the ambiguity between moderators and mediators. The same variable cannot be both. So in the MacArthur model, here we get to where the controversies are coming from. The MacArthur model, you cannot do moderator-mediator analysis in cross-sectional data. No. In the Baron and Kenny, you do it. In the MacArthur model, there are no causal inferences from correlations. In social psychology, you often do make causal inferences from correlations. In the MacArthur model, the same factor cannot be both a moderator and a mediator of the same T and O in the same population. And here's where the Baron and Kenny people say, ha-ha, we gotcha, because social psychology can moderate and mediate the effective treatment. And I say, no, you don't, because social support measured prior to randomization may moderate the effective treatment. However, social support measured during treatment to be a mediator would have to be the change in social support during treatment. And the change in social support and the baseline social support are two different constructs. So no, the same variable cannot both moderate and mediate. Let me give you some practical examples. The MTA was a study on, actually UCSF was one of the sites, I believe. Glenn Elliott was here at the time and was the PI here. It was a multi-site randomized clinical trial for kids with ADHD. There were 4 treatments: drug, behavioral, combination, community control, which is treatment as usual. The graph on the left, this is reduction of symptoms over the 14 months of treatment. The graph on the left looks pretty much like what it would be for the total sample. There's no difference between drug and combination, and there is very little difference, no significant difference between the behavioral or the psychosocial intervention and the treatment as usual, but a big separation between the two of them. But in fact, the graph on the left is for the 2/3 of the sample who did not have a diagnosis of anxiety disorder at baseline. Comorbidity is strong here. And the graph on the right is for the 1/3 that did. And you'll notice that the patterns are very different. And this is an example of what you see if you have some baseline variable. Here it happens to be comorbid anxiety disorder that changes things. It does not change the relationship between the drug and the combination. They remain virtually identical. But it does change the effectiveness of the community control relative to the other three. And this becomes a very important issue in terms of making recommendations. Actually, let me go back there for a second. I actually think from things that came out later that comorbid anxiety disorder at baseline is proxy to something else. And the something else that it's proxy to is psychopathology of the parents and the initial severity. There's evidence to show this. And this is very interesting because one of the people in our group was a pediatrician who said, does this mean that when I'm diagnosing kids, I've got to diagnose their parents first? And everybody in the room said, that's exactly what it means. This is an example of a mediator. And a mediator, as I mentioned earlier, is compliance. It was actually whether the treatment was delivered as intended was their term. And you can see that for the medication group, compliance versus non-compliance made a big difference. For the, over the right-hand side, the psychosocial group, it made very little difference. And for the combination group, it made very little difference. This is interesting because the people who were advocating psychosocial treatment really believed that the reason that psychosocial treatment did not do well relative to drug treatments was because of compliance. But in fact, that's not the explanation, because if we could get everybody to comply to everything, in this case, it would have increased the preferential effect of the drug over the psychosocial treatment. The one in the middle is interesting only because the compliance here was heavily dependent on the compliance with the behavioral aspect of the combination. So that's, I think, why you see them so close together. Here's another controversial issue. Problem of adjusting for covariates or confounders. Let me start with the definitional problem. The definition of a confounder requires that it be correlated at the population level with both things that are being confounded. So a baseline factor in a randomized clinical trial cannot be a confounder of the treatment effect. Why? Because with randomization, there is no correlation between the baseline and choice of treatment. For one study, you may find a correlation, the sample correlation, but if you repeated the study over and over again, it would disappear. The same variable does not come up significant in all these replication studies. It is not a confounder. So when you get reviewers coming back and saying you've got to consider all these confounders in a randomized clinical trial, think of some nice polite way of telling them to look it up in a dictionary. You should not be adjusting because you think they're confounders. The baseline factors fall into three groups. So the ones who are irrelevant have nothing to do with the treatment, they have nothing to do with outcome. You shouldn't be adjusting for them because the only thing you accomplish by adjusting is losing power. And if you adjust for more of them, several of them, and they're kind of collinear, you may actually be compromising the validity of the study as well. Non-specific predictors are baselines that do not moderate the treatment, but do predict the outcome. It's not a good idea to adjust for those either, because if there are more than one of them, you go into collinearity problems. And with a moderator, to make all the possible adjustments means that you're going to have to adjust for so damn much, you're not going to be able to get any study. So my strong recommendation is basically if you're doing a randomized clinical trial or a risk study, tell me first what the general effect is, and only later go on to tell me about the effect of various baseline factors and adjustments. So my recommendation is that I'm going to focus now on RCTs because it's clearer here, is that if I were looking for which treatments are better than which treatments, I would look for large, simple, randomized clinical trials. Adequately powered. I love multi-site studies. Simple means simple randomization to whatever treatments are there, and no adjusting, no controlling, no nothing. Just give me a good sample and tell me what the answer is first. Because the primary goal is the overall effect size. That's no covariance, and it's confidence interval. The thing I like about going back to multi-site trials, the thing I like about multi-site trials is that there's sort of an internal check on whether the effect size of treatment generalizes from one site to another, at least among the sites that are represented by the sites in the study. That gives me a lot more confidence. And I have to say, every time I have participated in a multi-site trial, I swear I'll never do it again, because it is so hard to do. And every time the next opportunity arises, I do it again, because they are so important. After you do a valid, adequately powered randomized clinical trial, and this includes all the ones that have been done in all the years past, what I would really urge is that you do exploratory analyses, hypothesis-generating activities, to try to find out which baseline variables are moderators of the treatment, if any. And if there are many of them, to try to develop an optimal moderator, meaning an optimal moderator would combine a lot of information to identify who is more likely to respond to treatment better than control, who is more likely to have a better response to control than to treatment, and for whom does it not matter one way or the other. But this is exploratory, which means that you would then have to confirm it in a second randomized clinical trial. But I will say this, and I would do it for the moment without proof. I am in the process of trying to get through these power calculations. What you really have to do is to validate that in a small RCT. I think it's small relative to the original. And that small RCT is specifically designed for the purpose of validating the moderator. It would not be as large as the initial randomized clinical trial. And then finally, if in that second RCT, what you might do is explore for mediators. And why have I put these separately? Because think about it. If I find a moderator of treatment response, it suggests that I have more than one population involved here. The mediators may be different in those subpopulations. So I'd rather establish the moderators first and then look at, at the mediators. As to how to get the optimal moderator, there are a number of proposals out there now. There's one major study, EMBARK, which is funded by the NIMH, that is developing methods to do this. And so give it a year or two and you'll find there are ways of doing this. And once you do that, go back to step one, because now we're talking about different populations and we're talking about possibly different treatments augmented by the knowledge of mediators. RDoC. I keep talking about risk studies. Marty?
If you want to have a discussion at the end, my disagreement was on the slide we just saw.
Okay, can we hold it to the end and then we'll...
No, I just wanted to earmark it.
Okay.
We've had the discussion before.
Okay. NIMH is putting primary emphasis on RDoC. And you've seen from my discussion, most of my discussion revolves around randomized clinical trials and risk factor studies and other studies of that type. But I want to point something out. And that is, if you do large, simple, randomized clinical trials, it would be a really wise decision to include biological markers at baseline. Genotype, brain structure function measures, biochemical measures, as well as the clinical, socio-demographic, environmental measures that may also, anything where you have a logic to believe that it may affect the relative impact of treatment versus control, should be measured at baseline. And then you explore it in the exploratory study that follows. And this might be very important. There we go. If you found moderators, there are a number of things that result. One of them is, basically, if you find that there is you can identify a subgroup of people that respond very well to treatment and another one does not, this might urge you to think about changing diagnostic criteria. This is the kind of evidence you might use to define either subtypes or to suggest division of a particular diagnosis. It also might give you clues as to the mechanisms by which the disorder develops, or the mechanisms for maintenance of a disorder, or how you might go about getting improvements in the disorder. But this is exactly what people are talking about when they talk about individualized or personalized medicine, to try to find those characteristics of patients that would motivate a clinician to make different treatment decisions for different patients. So this is not inimical to RDoC, but it is different from the RDoC approach. So my bottom line, first of all, I really urge you to say what you mean and mean what you say. Be very careful about your use of scientific language. Make sure it's consistent with scientific terminology. I think that any variation of this statement, that's the way we've always done it, is just poor science. We really do have to change. Methods that you learn in graduate school often prove wrong in the long run, and you're going to have to replace them, or non-optimal, and you have to improve them. And so basically, learning new methodology is a lifelong thing. If you're a researcher, you're constantly going to have to change and upgrade it periodically. And for me, one of the major impediments to progress are reviewers. In the past, I did a lot of reviewing for proposals. I sat on various review committees. I don't do that anymore, but I still do a lot of reviews of papers. And I still consult. I get very frustrated with some of my other reviewers. I'm sure they get frustrated with me too, because some of these problems are persistent because reviewers are requiring them to be persistent. I have always adjusted for all these baseline factors, so therefore you must adjust for all these baseline factors. Please don't disturb me with evidence that shows this is not a good thing to do. I don't know how we deal with that, except maybe come up with a way of rating reviewers and getting some of the really bad ones out of the way. But it is a major problem in doing this, and in implementing a lot of what I've been talking about, you're going to have to learn how to be judicious in addressing these issues when it comes to addressing them for reviewers of your own papers. Anyways, thank you. I'm Oh, Marty.
Well, we're predominantly talking to younger investigators, younger than Helena and I, which includes you.
What's your
and so I just want to say, since I said I disagree on that slide, everything Helena said is right as far as I'm concerned. Everything is right, including especially this last thing. And it's really, so what Helena is the proof doctor. So if you want to know what differences between proofs and a variety of pseudo-proofs and erroneous proofs, everything she said is really, take it really to heart and study it in designs and in research work. Do you want to go? Well, I'll go to where I disagree. Can you go back a slide?
Which slide was it?
Just go back and I'll say when.
Okay.
It's the one that, there we are.
Oh, the recommendations?
Yeah.
Okay.
Okay. I'm not the proof doctor. I would be the, so the reason I disagree is starting with a large, simple RCT is what you want to do to get a series of proofs. If you want to make discoveries in our complex field, especially dealing with psychosocial variables and the alleged biomarkers for psychiatric disorders that the RDoCs are arranging for us to find in some magical way, in the plethora of genes in the genome, and the plethora of interactions and the social memes, and the plethora of interactions in memory and emotion systems. For you younger people, I'd say start with really intensive case studies and find out what's going on in the complexity of change. And then because that gives you new variables. And then do some really quick and dirty local series of those and look for correlations without thinking you're proving anything, and don't worry about p-values, but look for the effect sizes. And then when you think you have something in this complex of variables, then design a slightly less dirty study, but keep a lot of variables in it so you can see what's going on. Then when you think you're developing some causation and new treatment to change the burden of illness, then do this.
And I don't disagree, and I'm going to expand this a little, and that is at your stage, the early stage of research, There are a lot of people who have data sets that have not been thoroughly explored. You don't have to go and collect all your own data. Secondary data is, any NIMH study technically is in a position now to share the data they're supposed to. So use other people's data to major advantage. This is exploratory data research, and without good exploration, you're not going to have good hypothesis testing. So I don't think we disagree on this. When I stepped off of council, which was 2008, they asked several of us to come in and sort of give our insights as to what was wrong with the review process. There were two statisticians there, Andy Leon was the other one. Both of us came down exactly on this point, and that is there had to be a lot more tolerance for exploratory studies. That in fact, a lot of randomized clinical trials, particularly, or hypothesis testing studies, were premature, badly designed, because they didn't have the information from them. But despite the fact that both of us asked for it, it really hasn't particularly happened. I also told them at that time, since I had retired a year before and I could afford to say this, retirement has its benefits, let me tell you. I told them that over the years I have been involved in a lot of K awards. I feel every K award should be exploratory. It should be looking at a new field and trying to understand what is known, what is not known, et cetera, in a new field. It should be exploratory, should not be hypothesis testing. And so much so that basically whenever I talk to K awardees and putting their things together, I told them to design the very best exploratory study they did, and then I told them to lie. I told them, pick out a hypothesis or two and present this thing as if it's a testing hypothesis, because it's not going to get funded if you cannot do that. But no, you are lying. And I said to the NIMH and all the council was there, including INSEL, and I said, I resent the fact that I was put in the position of having to tell my students to lie in order to get funded. This does not make any sense. Was there a question over here? Yes.
This is a practical one, Helena. In terms of the recommendation of doing a large RCT and appreciating the fact that, say, multi-site studies are funded by the NIH several millions, to test your primary goal, looking at the effect size, then you do exploratory moderator analysis from that data set. In your experience, do you know anyone who then went back to validate that moderator in a smaller RCT?
Yes,
and received
did.
funding from the NIH to do that?
Stewart did.
Excuse me?
Stewart did. Stewart Eggers did.
Which one?
He found that, I think it was comorbid depression at baseline, moderated the effect of treatment. I can't even remember. One of the reasons that I am very good at confidentiality is I always forget the details. I can remember all the statistics, I can't remember the drugs.
Right.
Anyway, for whatever eating disorder that was, he found the treatment was much more effective if they did not have comorbid depression.
Right.
And put in another randomized clinical trial in which he actually included a component that addressed the depression in order to try to bring it up. It's rare.
Right.
Yes.
So, well, first of all, thank you very much for your wonderful talk. I have been a fan of your work, so it's really wonderful to meet you in person. And I agree with you everything on every thing that you have said, and especially the large simple RCT are the best, meaning that the whole purpose of randomization is based on the randomization. And it's only possible with a large sample. If you have a small sample, the randomization is going to fail. So you're, again, talking about the principle that when we do the study, we've got to stick to the principle. I know you're going to get this question. It's a very stupid question, but I just cannot help myself. It's also based on the effect size and everything. How large simple RCT is going to be large enough? Just a rule of thumb. It's just, I know it's.
I have Stewart's run in the 200s.
Yeah.
Stewart's are the silkiest randomized. They're silky and rough for me. And multi-site.
3 sites.
3 sites, and about 200 or 300 patients, and it works.
220.
The couple of the others have run in the 500 to 600s, but they were really overpowered. They could have done with less. So I think, basically you don't have too many sites, because otherwise you're going to build a lot of site differences into it. and you have a sufficient number at each site to really get a sense of what's going on at that site. And then my guess is that you're not going to do it with fewer than about 200. But
For two
I think,
treatments, right?
or 220, whatever.
But for 2 treatments.
2 treatments, yeah. However, and I will also add this, and that is, and this is not merely a multi-site study, if basically you have to go to 800 or 900 or 1,000 subjects, you've really got a lousy effect size. And it's probably not worth putting the effort into it. And this is very much against a lot of the RDoc stuff, because some of those genetic associations are really teeny, and they're putting a lot of money into increasing the sample size in order to detect these minuscule effect sizes. So there is a thing such as too large an effect size too. Yes?
Right, I have 2 questions. The first one being this sort of topic. If you are a senior investigator who can apply to the NIH for a large, simple RCT multi-site study that's adequately powered and has everything you want and costs a gajillion dollars for what can be intensive treatments, that's great. But for junior or mid-level investigators, you know, we have to often go in with a single site RCT, and Kevin has been trying to help me with this terribly underpowered study. We had high attrition. We just didn't get as many subjects through as we wanted, but the money has run out. You know, this may be a political question, sort of, but how do you deal with this issue?
I'm also going to give you a political answer, which is actually going to extend what you say. I don't think at your stage in the career you should be in a multi-site study at all. And the reason is that in order to progress in your field, you need publications with your name at the top of the list. And if you are a junior investigator in a multi-site study, the chances of your being a senior person, or even if you're a senior person being credited with that study, are really very small. So I don't think, I was saying a large multi-site study for clinicians to understand what the treatment effects are. That wasn't a recommendation that you should be doing multi-site studies. It is a recommendation that you should look to other people's multi-site studies for the information, but you're absolutely right. At your stage in the career, multi-site studies are not in the picture.
But then
They're great learning experiences, though.
Yes.
So if you can sit fly on the wall while other people are designing a plan, that's great.
She has a follow-up question.
Yeah, no, I hear you. I've learned a lot of things, some of them. But then I have these, single site studies that are just underpowered, and it's so frustrating. So you're saying go exploratory or look for some data that you can work with, and
including large multi-site studies that
afterwards, and skip that middle step of this
Oh.
single site, moderately
Or,
sized, but
yeah.
inadequately powered.
Remember, if you're doing a single site, going back to the question that was asked before, is how large is large enough? Basically, you should be able to get a moderate effect size in a clinical trial, not for a prevention trial, but for a treatment trial. You would get more than adequate power with 62, 63 subjects per group, so it's 120 people. So that is a large study, single site study.
Yeah.
Smaller than that, I would spend an awful lot of time trying to figure out whether there are ways that I could raise the power without increasing the sample size, multiple measures over time, more reliable measures, think very carefully about your design, etc. Get the power up as high as you can possibly get it. You don't want to spend 5 years of your life on a study only to get all non-significant results.
Too late.
Yeah.
But thank you.
This isn't the last time you're going to have to make the decision. So.
It's true. Lesson learned. But my other quick question was, given your discussion of p-values versus effect sizes and that kind of issue, which is, first of all, sample size also affects confidence intervals for your effect sizes to some degree, so you can get kind of stuck. But what about the comment of correcting for multiple comparisons, when you have a number of measures and some are hypothesis-driven, some are exploratory?
I classify, and I am well out of step with what a lot of people say on this, I classify any study, including randomized clinical trials, that have multiple outcome measures as exploratory, not hypothesis testing. The problem is that the correction for multiple testing corrects one problem, which is you're going to report that something is going on out there with less than a 5% error. However, the things that come up labeled significant are not necessarily the true positives, and the things that are negative are not necessarily the true negatives. I don't think you know what the answer is from that kind of a study. I am advocating those, I'm going back to Marty's point, I'm advocating those studies, but treat it as hypothesis generating. So do 10,000 gene loci, go ahead, do it. And then what you do is locate what you think the hot spots are and design another study to test only those hot spots. Small study to test the hot spots.
Tell a little story about that and volunteer you for coming back, Helena. May I volunteer you for coming back?
Oh, by all means.
Helena could do this, and we could do this here too. A foreign government was having trouble with their equivalent of NIMH funding mental health research. And they were saying, well, none of the grant, you know, these young people want to do a grant and they want a gazillion dollars, and we don't have a gazillion dollars. And no one's getting funded in the behavioral health field, medical things. Okay. So what can we do? So they asked a series of consultants from the United States, and they had two in 2 previous years, and they're still not funding the studies. And then they asked me if I would come and consult with the potential investigators who weren't getting their studies funded, who were basically academicians, and pretty young ones. But, I said, well, 2 people I really respected had already been there. What did I know that they didn't know? So I said, well, I'll play around. So the game I played was the investigators would come and present a design, and then they'd leave the room, and the group of people left in the room would make up data. And I would try and give them sort of good, you know, pretty good data. Their hypotheses were more or less right, but realistically, what they might get. And so they would put in their design, 50 subjects, randomized 25 to this, 25 to that, so whatever, and then they'd come back in the room and we'd give them the data. Well, here's the effect size. Kind of promising. P-value was 0.3, but the effect size was good, and 2 people died, you know, or whatever. And you are now 3 years older, and this cost you so many shekels, what wasn't Israel, so much dollars. And now what are you going to do? And usually we gave them 15 minutes to put another design on the board. And it was usually a larger one. It's going to cost you 5 years, $3 billion, and here's your results. What are you going to do then? You're now 40 years old. Well, I'm going to do this, and so it's fun. And they started getting grants because they stopped coming up with designs that weren't going to get them where they wanted to go, and they understood it's the real world. It's really frustrating. There was only so many shekels, and there was this all these obstinate people and reviewers, but they have to struggle with it. And I think we have to play that game now because our field's in a crisis.
Yeah, also the other thing in your story is they thought about what came next, not just new design, but what came next. And this is again going back to this business about the K Awards. Imagine what would happen if you finished the research in your K Award, and what would you do next? And if the answer is I have no idea in the world, your career may be held up for a couple of years while you try to decide. What you should have is some notion of, if I can answer this question, depending on what the answer here is, then what I would do next, and then what I would do next. And now you've set up your career trajectory for a lot of years. And that's really the ideal. Yes?
This is really just a semantic question, but I've heard about some people talking about adjusting for versus controlling for covariates. Can you speak a little bit to what?
Yeah, my definition of, and it corresponds to what's in the literature sometimes, because this is one of the ones that are disagreed. Is there a thermostat in this room? There must be someplace. If I control the temperature in this room, if I set the thermostat and every time it goes below a certain level, I put the heater on, and every time it goes above a certain level, I turn the heater on. I am physically controlling the temperature in this room. I am adjusting for the temperature in the room if I simply write down the temperatures, and then I use a mathematical model to try to figure out what happens as the temperature varies in this room. So technically, if you're throwing in covariates, you are adjusting for these covariates, and it should be adjusting for these covariates in this particular mathematical model, because if the model is wrong, the adjustment may actually do more harm than good. That's my distinction of it. I think it corresponds to Rothman's distinction, for example, too. Control really does mean physically doing something to adjust it. So if I wanted to control gender in this study, I would sample equal numbers of men and women. I would not just throw a gender in as a covariate. I will bet in the next couple of days, if I succeeded, you're going to have a lot more questions. Thank you very much.
Thank you.